All right, so if you guys are on Desmos real quick, let's say that we've got the square root. What's the square root of 9? 3, right? Okay. What is the square root of 16? 4, right? And we keep doing that game. We square root of, 25 is 5, all that kind of stuff, right? Okay. What I'm going to do real quick is I'm going to just replace this 9 with the letter A, and it'll make sense here in a moment. Take 9 on your calculator. Okay, so hit 9, and whatever calculator you're using. Now, we're going to try typing in an exponent. So with Desmos, if you hit Shift and then 6, it'll create an exponent. And now instead of like the square root, I'm going to type in an exponent of a fraction. I'm going to type in 1 over 2. And what does it give you? Okay, so it gives you the square root of 9. It gives you 3, right? Well, let's see if that's a pattern, because that could be just like a coincidence, because like 2 plus 2 is 4, and 2 times 2 is still 4, right? So it might just be a coincidence that that's just one number where two different operations, like adding or adding and multiplying, give the same response. But let's try 16 then. So give me 4. So give me 25 raised to the 1/2 power is 5. Is that square root of 25? So let me put A in here real quick. And now what's nice about this is I can say A equals, okay, give me any number now. Okay, 25, give me another number. 8, give me another number. Okay, 25.832. Oh, hit enter. 0.83217. Okay, pretty random number, right? Would you agree that by showing you the square root of A up top and A raised to the 1/2, and just typing in a pretty random number, and they still both turn out to be the same thing, that we can make the argument that these two things, that one and that one, are equal to one another? They're alternative ways of writing the same thing, okay? So that's a little bit of by seeing previous facts, maybe a little bit of a proof of why I can rewrite the square root of A as A to the 1/2. Now, let's go a little bit further with this, because you guys have done this a little bit or you should have done a little bit of this in algebra. If we have a square root, like let's say the square root of, let's go, 48. Okay. And I want to simplify the square root of 48. Did you guys do this last year? And I know we might be off a little bit with our knowledge about radicals because of the quarantine last year or whatever. But did you guys simplify that and say, okay, well, radical 48, that goes down to 2 and 24, and that goes down to 2 and 12. Have you ever done this before? Yeah. Okay, so go down to 2 and 6. And then you wrote this as, you can write it as radical 2 times radical 2 times radical 2 times radical 6, right? Or you can write it, there's a lot of different ways that we write this. We could do it this way. 2 times 2 times 2 times 6. Now, here's my argument. This is kind of a proof of this procedure right here. Why are those two things the same? Why can I write, because they look different, right? So you were taught last year that if you have a radicand, this number underneath is a radicand, okay? That is a series of factors, so it's essentially a product. Then you can rewrite it as a product of those individual radicals, okay? And I want to talk about why, okay? Because you were told that you can do this, right? Okay, and you probably even said, okay, well, let's simplify this a little bit further, and you would write this as 2. Those don't have a pair, so then you say radical 12, and that's my final solution, right? Okay. And actually, my fault, because 6 goes down a little bit further, doesn't it? 6 goes to 2 and 3. Because this should be, so let's put that 2 here and a 3 here. Let's replace this with 2 times a 3. Okay, so now you got a pair of 2's, that can come out as a 2. You got another pair of 2's, that can come out as a 2, and then you got your radical 3. So it's actually 4 radical 3 is the actual simplified answer, okay? If that doesn't make sense right now, that's okay. And how we simplify, we'll spend a lot of time on that this year. But the question is, why do I know that that is the same as that? And it's because of what we were talking about right here, okay? If I ask you the square root of, let's just do, if I write this one, the square root of 2 times 2 times 2 times 3, well, that is equivalent then, instead of writing a square root, it's equivalent to writing it this way, 2 times 2 times 2 times 3 raised to the 1/2 power. Does that make sense? Okay. Do you guys ever remember seeing something like this? Like if I have like a squared b to the third, and I square that, okay, let's just think about what that means. We have a squared b to the third times a squared b to the third, right? Well, what's a squared really mean? Does it mean a times a? And b to the third means b times b times b, right? And then a squared is a times a again, and b to the third is b times b times b again, right? So here's my question. How many a's do you have being multiplied together here? 4. Can you rewrite that as a to the 4th? How many b's you got? Can you rewrite that as b to the 6th? Does that make sense? So when I have something like this, instead of writing it out like that and then expanding like that and essentially counting how many I have and that becomes my exponent, what can I do with that number and that number? Multiply, make a to the 4th, and then that number and that number gives me b to the 6th, right? So that in itself is a little is deductive reasoning. How do I go from this, or how do I go from this left-hand side straight to this right-hand side? The logic of why I can make that jump is this stuff right here. So are these exponents up here 1? Okay. So can I do the same thing? Can I go 2 times that, or this 2 raised to the first, so take this first power, multiply it by half, you can get 1/2, right? So we get 2 to the 1/2 times then another 2 to the 1/2 times another 2 to the 1/2 times then 3 to the 1/2, right? Does that make sense? But what do we say that anything raised to the 1/2 was the same as? The square root, right? So initially we started here and I rewrote things this way. Now we've got a bunch of things raised to the 1/2. Let's rewrite it using the square root technique. So now I can rewrite this as radical 2 times radical 2 times radical 2 times radical 3. And you can see then that we can go from the square root of 2 times 2 times 2 times 3 is equal to the square root of 2 times the square root of 2 times the square root of 2 times the square root of 3, right? Does that make sense? And that logic is the proof of why we can do that. Why you've been told, well, if you got multiplication underneath, you can just separate them. And that's what you're probably told in 9th grade. Maybe 8th grade for some of us. But that is the algebraic proof of why we could do it. Does that make sense? Okay. So that's what we're interested in. Everything that you've been told, okay, and if we have time, maybe early next week, we'll do division by 0 and say, well, I've been told that forever, but what's the reason why? We'll investigate some of that stuff, okay? But deductive reasoning allows us, and there's other types of reasoning, but deductive reasoning allows us to prove a lot of our facts, our rules and laws inside mathematics, okay? There's another type of reasoning called inductive reasoning, which you probably use the most in algebra, where you make a pattern. You see a pattern. If I go like 2, 4, 6, 8, what's the next number going to be? 10, and then 12, and then, right? So you're using that pattern to make a judgment about what's going to happen next. That's called inductive reasoning, okay? But deductive reasoning, by definition, sometimes they call it logical reasoning, is the process of reasoning logically from given statements or facts to a conclusion, okay? So logic is kind of the way we think, okay? It's using previously known facts to build something that can prove a new fact or create a new fact. Okay, so it's the idea of making a conclusion based on already known facts, such as definitions, postulates, and theorems. So that's why I harp all the time on knowing what our theorems say, what our postulates say, what our definitions say, because they're used to create new theorems. Does that make sense? New rules. And if I don't know the previous rules, there's no way I can build to create the new ones. It's like going into, like if I was the first day of high school, I jumped straight into the Spanish 4. Am I going to swim in that? Am I going to struggle in that class? Because I haven't built my knowledge for Spanish 1, Spanish 2, Spanish 3, right? So it's the same idea. If I get into chapter 7, and I really haven't been focusing on this class for 6 chapters, chapter 7 is going to stink because everything that's in 7 is built off of 1, 2, 3, 4, 5, and 6. Deductive reasoning, short of it is we're going to be using things that we already know to make a conclusion, things that we already know to be true. Okay, so there's 2 laws that exist inside the deductive reasoning approach, and they're called the law of detachment and the law of syllogism. And you guys have used, they're weird words, but you have used these all the time for your entire life. Okay, so here's the question. Okay, it says the property says if the hypothesis of a true conditional is true, then the conclusion is true. And that to me just sounds like they put like 5 words together and said true like 6 times. Okay, it's kind of, I think it's a hard law to kind of understand. But basically what it says is if I give you an if-then statement, okay, let's say if it is raining outside, then the ground is wet. That's an if-then statement, right? If it is raining outside, then the ground is wet. And then I give you another statement that says it's raining today. Does that match the if part of my if-then statement? Or my if-then statement said if it is raining, then the ground is wet. And then my new statement says today it's raining. Do those match? Let me write it down. Let me type it out so you can see it visually. It might be useful. So if it is raining, then the ground is wet. That's my conditional, right? All right, so my next statement I'm going to give you is that it is raining. Does this right here, does that statement match that? Okay, so that's what they're saying here in this phrase. It says if the hypothesis of a true conditional is true. That phrase right there is the idea of me looking at this true conditional in these 2 statements together and saying if these match, okay, which that is true right now, right? They match. Then it says the conclusion is true. Okay? Then for today, since it's raining today, I can make the argument about today that the ground is wet. Does that make sense? Okay. Now here's where that might seem very obvious, but what if my second statement says it is or let's say the sky is blue. Does the sky is blue, does it match with it is raining? No. So I can't make a conclusion about whether the ground is wet or the ground is not wet. Does that make sense? You've all experienced when the ground was wet, the sky is blue. You've all experienced when the ground was dry and the sky is blue. There's nothing that we can definitively argue that is occurring here because this is not true. Okay? This does not match this true hypothesis, so I can't make this conclusion. It doesn't mean the opposite of that conclusion. It doesn't mean it's false. It just means I can't make an argument. Does that make sense? Okay? And this is stuff that we do all the time. Okay? If it is 1 o'clock, then we go to lunch. Okay? When the bell rings, what's that going to tell you? Or when my phone goes off, what's that going to tell you? It's 1 o'clock, right? And if it's 1 o'clock, then you guys get up and go, right? Because you've met, your second statement has met the true hypothesis of a conditional statement. Okay? So that's kind of what this is saying. It says, in order to use this law, you must first identify the hypothesis of the given true conditional. It says a second statement is then given, If that statement matches the hypothesis, you can make a valid conclusion. Okay. The way I don't know if this is the way it's supposed to be like written, okay, or why it's named this way. But the way I think about it is that it's called the law of detachment, because this is kind of detached or uncoupled or taken apart from this original if-then. Does that make sense? So if this is detached, and I can say, okay, it's detached, does it match here? Now I can attach back to it the true conclusion for that particular situation. Just the way my mind kind of organizes the difference between the law of detachment and what's going to be called the law of syllogism here in a minute. The law of detachment example, okay, says if a student gets an A on the final exam, then the student will pass the course, okay? So let's talk about the hypothesis. What's the hypothesis there? Which one of those portions is the hypothesis? Okay, so we've got that is our hypothesis. So here's our second statement. Okay. Now, like I said yesterday, we used the word verbatim yesterday. These don't have to match verbatim. They don't have to be word for word. Okay. But we see it says Felicia got an A. Okay. We can probably make the assumption that Felicia is the student that it's talking about in the if statement, right? Okay. Final exam. Well, it says history final exam. A little bit more specific in the second statement. But can you see if those two things match? So what is now the conclusion you can make about Felicia? She passed the course, okay? Because those match, she passed the course. Well, if I said something like this, let's say my second statement was Felicia got a B on her exam, final exam, okay? Does that match the original given if part? No. So we can't say anything, okay? She might have passed. You know, B is pretty good on final exam, right? But what if she got Fs for 4 9 weeks, okay? That's all going to balance out to fail, right? Okay? So there's no specific conclusion we can make, okay? Doesn't mean she failed. Doesn't mean she passed. We don't know, okay? So that's the law of, does that make sense about the law of detachment? Okay? All of your procedures in algebra are usually presented that way. Did you guys do absolute value last year? Okay. So you had a rule in algebra that says if, and I'm just going to say, just to make it easy, we'll just write the word expression here. If we had an expression inside the absolute value bars, and it was equal to C, okay, then what you do is you take your expression and you set it equal to C, and then you write the word or, and you take your expression and you equal negative C, okay? And the logic of why you do this is because if I'm talking about a distance away from 0, that's what absolute value is. I could be to the right of 0, I could be to the left of 0, right? So this equation is going to give me the values that put me to the right of 0. This one's going to put me to the left of 0, okay? But once you knew that, once you learned that, now we go through our practice examples and we say, okay, well, 2x plus 3, that absolute value, is equal to 7, okay? This is your law of detachment. Does that there match to that? Yeah, right? You've got an absolute value on the left-hand side all by itself. You've got your equal sign, and then you've got a constant of 7, right? So because that matched, you can make this conclusion about your specific problem. So the conclusion was, well, you're going to take 2x plus 3, set it equal to 7. You're going to write the word or. You're going to take 2x plus 3, set it equal to the opposite 7. And you would solve both those, right? Okay. Do you remember what your rule was? You were probably just told that you had to do this first before you can start applying that idea, before I can make the C term negative. You remember that I was saying you had to isolate your absolute value bars? You had to get them by themselves. Okay, let's think about why. If I said like absolute value of 2x plus 3 and then minus 4 was equal to 7, does that right there match that right there? No, because the absolute value expression is not by itself, right? So you could, and people that would get this wrong, they would just say, well, I've done it this way for so long, I just take what's there and basically get rid of the bars, and then take what's there, get rid of the bars, and then make the C negative, right? So the number one wrong answer that people put here is they go like 2x plus 3 minus 4 equals 7, or 2x plus 3 minus 4 equals negative 7, right? But you can't do that because you don't have the law of detachment working yet, okay? You have to move this 4 over. Now you can go 2x plus 3 equals 11 and 2x plus 3 equals negative 11, right? Does that kind of make sense? So that's just one example of algebra that we've gone through, rules that we've been provided with, and how we know when to use them and when not to use them. Okay, so our specific problem has to match the hypothesis of some law or some procedure that's been laid out for us to kind of navigate through that algebra. Okay, does that kind of open our eyes to some stuff? Okay, I think a lot of things we do is a little bit backwards in mathematics, because you have the ability, you have the capacity at like the 9th grade, 10th grade, 8th grade level to do a lot of calculations, but you at that time maybe don't have enough math to really understand or learn why those calculations can take place. Okay, you guys know what the quadratic formula is? You guys know this thing here, the opposite of b plus or minus b squared minus 4ac all over 2a? You've never seen that? Do you guys remember taking something like x squared plus 7x plus 10 equals 0? And rewriting that as x plus 2 and x plus 5? And that gives you x equals negative 2 and x equals negative 5. I'll teach you how to do this at some point this year. But those are the values of x that will go in here. And when I evaluate, I get 0. Okay? This thing is a shortcut for getting negative 2 and negative 5. And actually, in this case, it actually takes a little bit longer. But this thing will factor any quadratic equation you ever come across. Okay? And now, it could have been because of the shortened year last year that you haven't seen that. But usually you're introduced that in, Algebra 1. But it's not until my college algebra students, which is a college class, they get college credit for it, we just talked about the why of that about a week ago. Okay? So a lot of times early on in your math careers, you're told things, you're shown things, you're able to take a formula and fill things in. You're able to remember I'm not allowed to divide by 0. But it's not 2, 3, 4, maybe sometimes 5 years later that you actually have learned enough math that actually allows you to actually investigate why those formulas worked or why that law was set up the way it was. Does that make sense? My big thing, and that's what this class is about, I think. I mean, we're going to learn stuff about shapes and all that kind of stuff and triangles and all the relationships. But my hope is that maybe the number one thing that you guys get as students in this class is that no matter what you are doing in a math class or a science class, that you just don't take a teacher's word for granted, okay? Just because he said it, because he's got a degree, he might have 2, 3, 4 degrees, whatever, doesn't matter. I want to know why. I'm not going to take anybody's word for it. Does that make sense? Okay? I talk with my stats kids all the time. If I'm just a blind observer and I just go about my day and I watch the media and I read newspapers and I do all that kind of stuff and I just read and take the media's word for what they say, I could be completely fooled by people that are publishing things. Does that make sense? I want to investigate a little bit. I want to do a little bit of digging and figure things out for myself. They're giving me information, but I need to know whether it's good information or not, right? You guys have been told not to use Wikipedia in your classes if you're doing research. Why? Why shouldn't I, as a teacher, let you use Wikipedia? Yeah, anybody can go. That's a public, like editing. Anybody can be a source on there. Okay, I can go in there right now and I can edit something about whatever. Maybe we're talking about Abraham Lincoln. I go in there and I can edit that he was born in 1400. He was best friends with Christopher Columbus. Okay, that's total false, right? Total lie. But I can do that. Okay. Now on the other hand, there's a lot of really, really, really good stuff in Wikipedia, right? Okay. So if I'm ever asked you to use like research or something like that, I would open Wikipedia up to you, but I wouldn't let you use it as like maybe a primary source. I'd let you go use it and then make sure, okay, double check those facts. Okay. You see that, Abraham Lincoln was born in 1400 and he's best friends with Christopher Columbus. Can I find that somewhere else? Is it true? Okay. And those are things that you got to realize, you got to think about in everyday interactions. I told my kids the other day in stats, if we're looking at, let's see here, and just how we can be manipulated very easily by publications, by the media. Look at those two graphs. Those talk about like yearly sales and some business. And I've got highlighted on there the same ordered pairs, okay? But if you look at the y-axis on the first one, it goes from 0 to 800, right? The y-axis on the second one, it's broken there at the bottom. It goes from 350 to 700. But in that second one, does it make it look like my sales have increased dramatically from October to December? But not so much in the first one. I can see there's an increase in that first one from October to December, but it doesn't look like it's as great as that second one. So if I'm a person that's trying to, try to persuade somebody maybe about how good of a salesman I've been since October, maybe I give them that second graph because it's a little bit misleading, isn't it? Okay. So I want to investigate. I want to ask questions like why. I want to look at the minor details like that. Turn that off for today. Look at this one. This is the same exact information. Okay. In that top graph, we've got it's sales again. Okay, by year. If you look at that top graph, the y-axis has been manipulated. There's 200 units between the 0 on my y-axis, and I think it's 200,000 there. But then between every other mark, it's only 50,000. Does that make sense? Where it makes it look like that third rectangle, which is talking about the year 2017 sales, it looks like almost no sales took place, right? But if I make the y-axis consistent, this is what this column should really look like. This isn't false data. Okay, it's true data, but it's a little bit misleading, right? It's a misrepresentation of the data. I want you guys, as you leave this class, not only to know some geometry, pick up some more math, some more algebra, that kind of stuff, but have that ability or that desire to ask why or to do a little bit more investigation. And I think deductive reasoning and analyzing this stuff through deductive reasoning will kind of assist in that. Here's another example. It says if a ray divides an angle divides an angle into two congruent angles, then the ray is an angle bisector. Okay? So again, the if part would be that guy there, correct? Okay. Does this match that? This is my second statement. Okay. What is that symbol right there talking about? It's a ray, right? Okay. We got the word divide, so that's good. Okay. What is that symbol? That's an angle. And what are we saying here? Okay, so how many angles you got here? 2. Are they 2 congruent angles? Okay, so does that match then what we're saying here? Yeah, it matches the if part. So if it matches the if part, what can you tell me about this specific ray? It's an angle bisector. Remember, if this is true and it matches the if part, then you can make the conclusion about that object in that statement. Okay. If two angles are adjacent and they share a common vertex, this is one that people want to. You heard me the other day say mathematics, we want to flip everything and say everything is reversible. Okay, so we want to say, like, if two angles are adjacent and they share a common vertex, and then they want to flip and say, well, if they share a common vertex, then they must be adjacent, right? But that's not true. That's actually false. Yeah, there's more to it. So if I have that says if two angles are adjacent, then they share a common vertex, does that match the highlighted text in the if-then statement? No. Okay. The highlighted thing says you have two angles that are adjacent. So there's no conclusion I can make about angle 1 and angle 2. And because there's no conclusion, does that mean the complete opposite, that they're not? No. Okay. We're going to talk about things all year long. We're going to try to prove shapes, and we specifically talk a lot about triangles. And I'll give you two triangles, and I'll ask you, demonstrate whether they are congruent, if they are congruent. Okay, based on the information I give you, are they congruent? And you'll be able to say yes or I don't know. Okay, because even though I tell you something about a shape, and I give you enough information, but you can't narrow it down. Say this. Well, for instance, let's say I think this might be, just to see an example might be better. Let's say I give you this triangle here, and I tell you that this is 60 degrees, and let's say this is let's see here. Let's do something like that. You guys know what? If I have two sides in a triangle that are congruent, so those markings show me they're congruent, right? So I'm going to say that left side and that bottom side are congruent. We know that to be what kind of triangle? If you have two sides congruent. Isosceles. Okay? Now, here's my question. Is that also an equilateral triangle? How many sides do you need to be congruent to have an equilateral triangle? 3, right? Equilateral, lateral means side, so equal means 3, so you need, or equal means the same, so we need 3 sides to be equal, okay? Do I have that up there? No, okay? So can I say that that is equilateral? No. Can I say it's not equilateral? Well, here's the argument. I don't, just because I can't say it's equilateral doesn't mean I say that it's not equilateral. Does that make sense? Okay? Because here's the thing. If these sides are congruent, that means these angles here are congruent. So they're both 60. And when it's all 3 or 60, it's equiangular, and equiangular triangles are also equilateral. So that is indeed an equilateral triangle. But based off the initial information I gave you and your current knowledge, all you could say is, I don't know, right? You don't say the complete opposite. If it's, no, I don't know if it's equilateral, does not mean it is 100% not equilateral. You just can't make a conclusion. Does that make sense? Okay? If you don't know something, you can't make an assumption. Okay? It's all right. Just want to go off the information that we know. We'll stop there. Okay? No homework tonight.